point 3 is solubility. When a substance is soluble, whenever it's dissolved in another solvent. So the solute must be dissolved with other solvent. Okay. For example, if you mix salt with water, the salt is completely dissolved in the water. So solubility refers to the dissolution process. Okay. The solute must be dissolved. For example, bromine is soluble in methylene chloride. ሌላ ምሳሌ ለመጥቀስ ያህል ኦይል ኢን ዋተር ብንወስድ ኦይል በዋተር ላይ ሁለት ዲስቲንክት ፌዝ ነው የሚሰጠን። ስለዚህ oil is insoluble in water ነው የምንለው። Okay, so it must give a uniform, or there must be some dissolution in order to say this is soluble by the solvent this. Okay, እንግዲህ solubility ላይ ሁሉም substance dissolve አይሆንም። Okay, አንዳንድ substance dissolve ይሆናሉ፣ አንዳንድ ደግሞ dissolved አይሆንም ማለት ነው። So solubility refers the degree the dissolution process. So saturation and solubility, depending on this degree of solubility, we can classify solutions as saturated solution, unsaturated solution, and supersaturated solution. Saturated solution is a solution in which the dissolved and undissolved solids are in dynamic equilibrium. So at equilibrium ሲሆን ምን እንላለን? The solution is saturated. ወይም በሌላ ምሳሌ extra solute ብንጨምር the solvent is not capable dissolving the solute. Okay, because it has it is equilibrium point. So a solution in which it reaches its equilibrium is said to be saturated solution. No more solute is dissolved in any given solvent. In the case of unsaturated solution, unsaturated ላይ እንግዲህ the solvent is capable to dissolve extra solids. Okay, additional solute ቢጨምሩ at a given temperature and pressure solution dissolve ይሆናል ማለት ነው። So in that type of solution is said to be unsaturated solution. So the third type is supersaturated solution. እንግዲህ supersaturated solution is a solution that can sometimes be prepared by saturating a solution at high temperature. At high temperature የሚለውን እንትኑሰዱት it is at high temperature. Saturation point ደርሷል ግን at high temperature ላይ extra solute dissolve ማድረግ ይቻላል. So you can get supersaturated solution just at high temperature ማለት ነው። Okay, extra solutes can be dissolved because of it is high temperature. All right, so እንግዲህ እንደየ solubility ዲግሪያችን unsaturated, saturated እና supersaturated solution ብለን ልንገልጽ እንችላለን። Okay, equilibrium established ካደረገ saturated ገና more solute dissolve የማድረግ አቅም ካለው unsaturated solution ይባላል። Still extra at higher temperature or at different state variable temperature pressure በመቀያየር extra solitoችን dissolve ካደረገን ያ አይነት solution supersaturated solution ይባላል ነው። honey is a good example of naturally occurring supersaturated solution. እንግዲህ ማርን ብትወስዱ naturally supersaturated solution ነው ብለን እንችላለን። Okay, supersaturated solution are unstable, and addition of acid crystal of solute will generally cause all of the excess solute suddenly crystallize. Right, እንግዲህ drop የሆነች amount solid የሆነች seed ብትጨምሩበት እሷን ተከትሎ crystallize ይሰራል ማለት ነው solution, because it's initially supersaturated solution ስለሆነ። Okay, scratch ብታደርጉ ያማሰላችሁ በግላስ ሮድ የሆነ ስክራች ስታረጉ ሲድ ይሰራል ሶ እዛ ላይ ሶሊዲፋይ መሆን ይጀምራል ማለት ነው so in that case that type of solution is already super saturated solution ስለሆነ ማለት ነው this is it factors affecting solubility there are different factors but primarily there are two factors pressure and temperature pressure significantly affects the solubility of gases okay but has little effect on liquids and solids this is because that gases are compressible okay you can compress gases so that you can increase the solubility of gases in the liquid okay if you increase the pressure of gases above the solution obviously the gaseous particles will be dissolved in the solution okay so increasing pressure will increase the solubility of gases but liquids and solids little effect ነው ያለው because incompressible ናቸው pressure ብንጨምር solubility መጨመር አንችልም temperature ጋር ስንመጣ solubility of most solids increase with increasing temperature ስንጨምር solubility of most solids will increase እንግዲህ ቅድም ስኳር ብያለው ጨው sodium chloride የነዚህ solubility by increasing temperature the solubility of these solid substances would increase but the solubility of gases decreases gases ላይ ግን ተቃራኒ ኢፌክት ነው የሚኖረው okay ለምን temperature ሲጨምሩ gaseous molecule in the solution escape ያደርጋሉ እንጂ temperature ስንጨምር solubility favor አያደርግም So the solubility of gas always increases with increasing pressure. It's ብለናል ለምሳሌ soft drink ላይ ያው carbonated soft drink ብንወስድ at 4 pascal pressurized ስናደርገው the solubility of carbon dioxide would increase in the solution okay እንግዲህ carbon dioxide at 4 pascal ላይ በዚህ pressure ነው ማለት ነው soft ድሪንኮች ላይ carbon dioxide dissolve የሚያደርጉት ማለት ነው ኦኬ ሚሪንዳ ኮካ-ኮላ ሌሎችም soft ድሪንኮች ላይ ያው it is common that the carbon dioxide is dissolved in this soft drinks champagne beer ሊሆን ይችላል so this is possible just by pressurizing the carbon dioxide gas above the soft drinks at 4 pascal okay so that the gas carbon dioxide would be dissolved in the beverage so this mathematically can be expressed using Henry's law Cg is equal to Kh times Pg where Cg is the concentration of gas in the solution Kh is Henry's constant and Pg is the pressure of the gas above the solution we assume there is a solution the solution alemble we have pressure above it so if you increase the pressure at the top then the tendency of that gaseous particle to be solubilized in the solution is high or in other words the pressure is directly proportional to the concentration of gases dissolved gases in the solution okay እንግዲህ solution ላይ pressure በጨመርን ቁጥር ብዙ gaseous molecule በሶሉሽኑ dissolve ይሆናሉ ነው so mathematically Henry formulated this Cg is equal to Kh times Pg where Kh is Henry's constant it's dependent on temperature so Kh would be given and if the pressure above the solution is given it's possible to know that the concentration of that gases which is dissolved in the solution the last topic in this chapter is colligative property of solutions. Under this chapter, we have four properties or four colligative properties. Let me first define what colligative property is. Colligative property is a property which is dependent on a number, but not the identity or the kind of the substance. Alright, so ምን እያልኩኝ ነው? ይሄ colligative property, intensive property, extensive property እንላለን እንግዲህ በኬሚስትሪ እና colligative property refer የሚያደርገው properties which only depend on the number but not the kind or the identity of the substance. For example, vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure are some of the properties which is classed under colligative properties. Let me first see the vapor pressure lowering. Vapor pressure lowering የሚለውን እንመልከት. If we add an non-volatile solid, then the vapor pressure becomes lowered. እንግዲህ non-volatile solid ብንጨምር የሆነ solvent ላይ በፊት ከነበረው vapor pressure ይቀንሰዋል። Alright, now ለምን colligative property የተባለው ወደሚለው እንሂድ. If you add much amount of non-volatile solute, then much amount of vapor pressure is lowered. So this lowering effect is dependent on the amount or the number or the mole of the non-volatile solute added. እንግዲህ ብዙ non-volatile solute ከጨመር ብዙ change in lowering pressure ያሳያል. change in P high ይሆናል ማለት ትንሽ ከሆነ ትንሽ change in P ያሳያል. So the degree of lowering is dependent on the amount of non-volatile solids. Okay, that non-volatile solid B can be X, it can be Y, it can be Z. It doesn't matter, whatever. As far as it's non-volatile, then it lowers. This effect is pronounced. Okay, this effect would be demonstrated in all cases. Okay, non-volatile ይሁን እንጂ Xም Yም Zም ሊሆን ይችላል. So it's not dependent on the kind of the non-volatile solid is. What is important is that solid should be non-volatile. Non-volatile እስከሆነ ድረስ Xም ሊሆን ይችላል, Yም ሊሆን ይችላል, Zም ሊሆን ይችላል, any compound ሊሆን ይችላል. Okay, so ሁሉም ጋር ተመሳሳይ ኢፌክት ይኖራል ማለት ነው. ሁሉም ጋር vapor pressure-ን lower ያደርጋል. ብዙ ከጨመን ብዙ vapor pressure lower ያደርጋል. ትንሽ ከሆነ ትንሽ vapor pressure lower ያደርጋል. That's why it's said to be colligative property. Okay, the same is true for boiling point elevation. Because the vapor pressure low ስላደረገ boiling point ደግሞ ይጨምራል. So boiling point first define ማድረግ ያስፈልጋል እዚህ ጋር. Boiling point is a point. ስሙ እንደሚያመለክተው it is a point. Okay, ለምሳሌ ውሃ at STP ከሆነ 100 degree centigrade is the boiling point of water እንላለን. Okay, እንግዲህ at STP ከሆነ ነው actually at this atmosphere boiling point of water ብንለካ 93 እንደዚህ አካባቢ ነው ልናገኝ የምንችለው because at STP አይደለም standard temperature and pressure መሆን አለበት. So boiling point elevation እንግዲህ boiling point define ስናደርገው boiling point is a point at which the vapor pressure of the liquid is equal to the atmospheric pressure እንላለን. Okay, at that point እንግዲህ vapor pressure boil ስናደርግ vapor pressure of the liquid is equal to the atmospheric pressure ሲሆን boiling point attain አደረገ እንላለን. Now non-volatile solids ስንጨምር ምንድነው? non-volatile solids ስንጨምር boiling point-ን ከፍ ያደርገዋል ማለት ነው. It's because that it lowers vapor pressure. The vapor pressure lower ያደርገዋል ካል እና boiling point define ስናደርግ ደግሞ boiling point is a point at which the vapor pressure of liquid is equal to the atmospheric pressure can. So it's a direct consequence. Okay, vapor pressure lower አደረገ ማለት boiling point ደግሞ ከፍ ያደርገዋል ማለት ነው. And the other is the freezing point depression. Still, the addition of solute lowers the freezing point. The freezing point of water, for example, is 0 degrees centigrade at STP. So upon the addition of solids, the freezing point becomes depressed. It can be -1 or 0, it can be -0.5, or it can be -3 degrees centigrade. Okay, upon the addition of a solid, the freezing point would becomes lower. If one adds much solute, then the depression amount or the degree of depression becomes high. So it's dependent on the amount of solute added. That's why it is said to be colligative property. Osmotic pressure. Osmotic pressure is a pressure created because of concentration gradient. Assume there is a compartment that has low concentrated and high concentrated solution, then osmotic pressure would be created. So solvent molecules will migrate from low concentration to high concentration in order to dilute that concentrated solution. As there is a gradient in the concentration, so that osmotic pressure will occur. So we'll see one by one using examples. Rolt's law explains the vapor pressure of a solvent above a solution is proportional to its mole fraction in the solution. So let us see it. This is Rolt's law. It's talking about the vapor pressure of a solution. This is the vapor pressure in its pure form. This is the vapor pressure after the added solid. So the vapor pressure is equal to mole fraction of that solvent times the vapor pressure in its pure form. ምን እያልኩኝ ነው እዚህ ጋር? አሁን ውሃ ውሰዱት። ውሃ ፒውር ምንም ሳንጨምርበት ቫፐር ፕሬሸር አለው። እሱ ፒ ኖት እንለዋለን። then non volatile solute ከጨመርን በኋላ የምናገኘው vapor pressure አለ P1. So P1 is equal to mathematically mole fraction of water. ለምሳሌ አሁን ጨው ብንጨምር እንግዲህ ሶሉሽናችን ጨውና ውሃ ይኖራሉ ማለት ነው። So mole fraction እንግዲህ it's a fraction, okay? Mole of the solvent divided by total mole. Okay, x1 is the mole of the solvent divided by total mole. Total mole is the sum of the two, mole of solid plus mole of the solvent. So this is Rolt's law. So Rolt's law explains the vapor pressure. The vapor pressure. All right, let us see this. If this is the mole fraction, the mole of solute, mole of solute አለ mole of solvent አለ okay solvent አንዱን x1 አንዱን x2 ብንለው እንግዲህ ምንድነው የሚለን እዚህ ጋር solventun 1 ብንለው soluteን 2 ብንለው እንግዲህ this equation is talking about all the solvent, mole fraction of the solvent, pressure of the solvent in its pure form, pressure after added the solid of the solvents. ስለዚህ ይሄ በሙሉ ስለ solvent ነው ያወራው 1 1 1 is talking about solvents. Now solid is 2. So mole fraction x1 ሲደመር x2 is equal to what? Is equal to 1. Yes, is equal to 1 because it's mole fraction. So x1 is equal to what? ይሄን ወደዛ 3 አንድ ሲቀነስ x2. So instead of x1 1 minus x2 ማለት ይችላል። So p1 is equal to p1 not እንግዲህ ይሄ ሁለቱን ሲያበዛ እንደዚህ ይመጣል ማለት ነው። ይሄኛው ወደዚህ ልውሰደው p1 minus p1 not is equal to minus p1 x2. So this is nothing but it is change in pressure. This is in pure form, this is after added. So change in pressure, change in P is equal to P1 no times x2, where x2 is the mole fraction of the solute. Change in pressure, the degree or the amount of pressure changed is equal to the vapor pressure in its pure form times the mole fraction of the solute in the solution. So using this equation, one can calculate how much pressure load, okay, upon addition of a given non-volatile solid. የሆነ non-volatile solid በመጨመራችን ምክንያት ምን ያህል pressure low ያደርጋል? Okay, እንግዲህ vapor pressure lowering colligative property ነው ብለናል። So ምን ያህል በአማውንት ደረጃ ምን ያህል የሚለውን የሚነግረን እንግዲህ ከሮልስ ሎ ይሄን ኢኩዌሽን እናገኛለን ማለት ነው። Okay, so as far as we know the mole fraction of the solute added in the solution, we can predict the change in vapor pressure. Example, let us see this. Calculate the vapor pressure lowering of a solution 20 grams of sucrose in 40 grams of water at 34 degrees centigrade. The vapor pressure of water is this at this. Okay, 34 degrees centigrade ላይ ነው እየተጠየቅን ያለነው. Given that at 34 degrees centigrade the vapor pressure ተሰጥቶናል in its pure form ማለት ነው ይሄ. So ምን ያህል vapor pressure low ያደርጋል ነው ነገርየው. Okay, 20 ግራም ስኳር 40 ግራም ውሃ ላይ ቢጨመር ምን ያህል vapor pressureውን የውሃውን ይቀንሰዋል. So the first step is to calculate the mole of individual solute and solvent. Now let me calculate the mole of water, that is solvent. 40 gram, I mean mole is given mass over molecular mass, so 40 gram is a given mass and 18 is the molar mass of water. So 40 ሲካፈል 18 ይሄን ያህል ሞል አገኛለሁ የሶልቨንቴ and the solute ደግሞ 20 gram ተሰጥቶኛል. We have 20 gram of sucrose, 20 gram of sucrose. ለሞላር ማሱ ለዚህ ሳካፈለው 20 ሲካፈል 342 ይሄን ያህል አገኛለሁ። እንግዲህ 342 is the molar mass. Okay, የሱክሮስ ሞላር ማስ ካርቦን 12 ሃይድሮጂን 22 ሃይድሮጂን 1 ኦክሲጅን 16 በዚህ በሰብስክሪፕት ውስጥ ታበዙት we get this molecular mass. So individual mole አገኘው። እንግዲህ እቺኛዋን ኢኩዌሽን ለመጠቀም ልብ በሉ change in P is equal to pure form ሲባዛ what mole fraction. Mole fraction ልብ በል x2 is the mole fraction of solute. Now የሶሉቱን ሞል ፍራክሽን በዚህ መልክ እናገኛለን ማለት ነው። እያንዳንዱ ሞል ካገኘው በኋላ mole fraction of this divided by total mole. So 0.0584 is a mole of the solvent, mole of the solute I mean, divided by total. Totalun ሁለቱ መደመር ነው. Okay, if you add ይሄ ሲደመር ይሄ 2.28. So this divided by this we get this amount. This is the mole fraction which is x2 ያልናት ነው። ስለዚህ አሁን ቀጥታ ማባዛት ነው. The pressure in its pure form times the mole fraction and we get this amount. So this is the pressure expected to lower upon the addition of 20 grams of sucrose on water. ይሄን ያህል vapor pressure low ያደርጋል. The second colligative property is boiling point elevation. Boiling point is a point at which the vapor pressure of the liquid is equal to the atmospheric pressure. Now, upon the addition of non-volatile solids, boiling point of a given solution becomes higher, and this process is said to be boiling point elevation. Elevate ያደርጋል። አሁን የውሃ 100 ዲግሪ ሴንቲግሬድ ከነበረ non-volatile solid በመጨመራችን ምክንያት 101 ወይም 102 degree centigrade ይመጣል ማለት ነው። Change in temperature is equal to Tb minus Tb naught. Okay, የጨመረው ማለት ነው። Okay, ኢኒሺያሊ የነበረኝ ያለ ይሄ non volatile solid ከጨመርኩ በኋላ ያለው boiling point ነው። ይሄ ከመጨመሬ በፊት ያለው ነው። So change elevation ምን ያህል elevate አደረገ ምን ያህል ጨመረ የሚለው non volatile solid ከጨመርኩ በኋላ ሲቀነስ non volatile solution ከመጨመሪያ በፊት that's the change in Tb. Now mathematically change in T or boiling point elevation is equal to a Kb times small m, where small m is the molality of the solution. Molality. Do you know molality? Molality is defined as the mole of the solute divided by kilogram of the solvent. So this is concentration unit, one of the expression concentration unit, molality. So this change in temperature, boiling point temperature, is directly proportional to the molality of the solution. Okay, times this constant Kb, molar boiling point elevation constant ይባላል። ይሄ constant እንግዲህ ይሰጣል። should be given. It's dependent on different parameters actually. Anyhow, the molar concentration affects the degree of elevation. Okay, small m ከጨመረ high amount ይሆናል ማለት ነው። ብዙ ነን ቮላታይል ሶሊድ ከጨመራችሁ elevation ብዙ ይሆናል ብለናል ቀደም። ትንሽ ከሆነ ትንሽ ይሆናል። So it's dependent on the molar concentration of the solute which is added. Let us example. Calculate the boiling point of a 0.33 m solution of a solid in a benzene if the boiling point of pure solvent benzene is this. እንግዲህ ቤንዚን ጋር ምን ሬት የጨመረው calculate the boiling point of the solution of a solid in benzene solid 0.33 molar concentrated የሆነ solute ቤንዚን ላይ ቢጨምር ነው የሚለው በስም አልጠቀሰው። now calculate the boiling point. okay, change መጀመሪያ እናገኛለን ከዛ ወደ boiling point እንሄዳለን። መጀመሪያ change in T ማየት change in T ማወቅ አለብን ማለት ነው። so using this molar equation, change in T is equal to this constant times this molality. now this is already given 0.33 molar ብሎኛል times this constant. This is the change. okay, ይሄን ያህል ሞላር ሶሉሽን በመጨመራችን ምክንያት ይሄን ያህል ቴምፕሬቸር ይጨምራል። so initially የነበረው ቴምፕሬቸር 80.1 ነው። የሚጨምረውን አማውንት አግኝቻለሁ ስለዚህ መደመር ነው። so this is the new boiling point after adding this molar concentrated solution. ይሄን ያህል concentrated molar የሆነ ሶሉሽን በመጨመሪያ ምክንያት boiling poinቱ ከ80.1 ወደ 80.93 increase አደረገ እንላለን። freezing point depression. እንግዲህ depression freezing pointን low ያደርገዋል ማለት ነው። all right, similar to the boiling point elevation there is an equation which is dependent on the molality of the solute. This is the equation. Change in Tf, change in freezing point is equal to Kf freezing point depression constant times the molality of the solid added. So let us calculate some examples. The freezing point of pure camphor having a molecular formula this C10H16O. እነዚህ ሰብስክሪፕት ናቸው ፓወርፖይንት ሲሆን እንትናለል ብሎ ነው። C10 10 ካርበን 16 ሃይድሮጅን አንድ ኦክሲጅን ያለው freezing point ይሄ ነበር ይላል and freezing point constant. Find the freezing point of a solution containing this እንግዲህ 1.5 ግራም ሶሊድ ቢጨመር ሞሌኩላር ማሱ 125 የሆነ አዲሱ freezing point ስንት ይሆናል? ወይም ይሄንን በመጨመር freezing point ከመቶ freezing point ከነበረው freezing point ወደ ስንት ይቀንሳል ነው? let us see it. okay, let us first calculate the molality of the solution. The definition: number of mole of solid divided by weight of solvent reported in kilogram. So this is the given mole, 0.012 mole. Actually it's not given. 105 gram of the compound divided by molar mass ይሄን ያህል ነው ስላለ ይሄ ሲካፈል ለዚህ given mass divided by molar mass would give us the mole. So mole divided by kilogram of the solvent. Kilogram of the solvent, I think it's given 35 gram. ወደ ኪሎግራም ስንቀይረው 0.035 ኪሎግራም ይመጣል። So mole divided by kilogram of solvent ይሄን ያህል ይሰጠኛል። So this is the molality of the solute. So change in T freezing point depression is equal to freezing point depression constant times the molality ጨርሰናል። ኮንስታንቱ አለ። So የሁለቱ ሲባዛ ይሄ ነው ማለት ነው። Now ምን ያህል ቼንጅ ያደረገ አይደለም ጥያቄው what is the freezing point ነው። Okay, let us see. So ምንድነው freezing point ዲፕሬስ ነው የሚያደርገው ዲፕሬስ ይቀንሰዋል ማለት ነው። So T minus TF initially this is the freezing point, then ይሄ ቼንጁ ነው ወይም so ይሄ ሲቀነስ ይሄ this is the new freezing point 1.5 ግራም 125 ሞላር ማስ ያለው ሶሊድ በመጨመራችን 13.6 ያህል ፍሪዚንግ ፖይንቱን ዲፕሬስ አድርጎታል ቀንሶታል። ስለዚህ ኢኒሺያል ከነበረው 13.6 መቀነስ አለብኝ። ኢኒሺያሊ 179.0 ዲግሪ ሴንቲግሬድ ነበር ሲቀነስ this would give the new freezing point of the solution. The last but not the least is osmotic pressure. The መጨረሻ osmotic pressure የምንለው ነው። So let us see this picture. Look, this is the concentration. The picture ላይ እንደምናየው this is at high concentration, this is at low concentration. So because of this concentration gradient, solvent molecules would migrate from low concentration to high concentration. ከዚህ ወደዚህ migrate ያደርጋሉ። ከዚህ ወደዚህ ማለት ነው። እነማን? solvent molecule. This is a semi-permeable membrane which allow to pass the solvent molecule but block the solute molecule, so that the solvent molecules naturally migrate towards from left to the right in order to dilute this. እንግዲህ naturally ይሄኛው at high concentration የሆኑ semi-permeable membrane ቢኖር solvent molecules ከlow concentration ወደ high concentration migrate ያደርጋሉ in order to dilute this concentrated one. This is a natural process, okay? So that after migrating እዚህ ጋር የነበረው እኩል height ላይ የነበሩት ሁለቱ ኮምፓርትመንቶች ይሄኛው ይሄን ያህል lower ይሆናል and this ደግሞ ይሄን ያህል ወደ ላይ ይወጣል ማለት ነው። So if there is a concentration gradient, osmotic pressure is created. So the driving force why the solvent molecule migrate from low concentration to high concentration is osmotic pressure. So osmotic pressure is a pressure created when concentration change or concentration gradient happened in two sides, when these two sides are separated in semi-permeable membrane. Mathematically, it is almost at dilute ከሆነ dilute solution ከሆነ osmotic pressure pi symbolized as pi is equal to nRT over V, which is quite similar with ideal gas law equation. PV is equal to nRT. Now the P is symbolized as pi in here. Osmotic pressure የሚለውን ለመግለጽ እንግዲህ ideal gas ላይ P የምናውቀው አሁን pi ስለ solution ነው እያወራን ያለ ነው፣ liquid solution. But the equation is similar. Ideal gas equation ላይ PV is equal to nRT ስለ gas ነው የምናወራው, but here it's osmotic pressure. So osmotic pressure is equal to nRT over V. But what is N over V? N over V. N is the number of mole of the solute which is added into the solution or which is present in the solution, and V is the volume. So N over V is simply C. C is concentration. C RT. Okay, RT. C RT. N over V number of mole divided by volume in liter ካልኩ molarity ነው ማለት ነው። See, so N over V is nothing but it is capital M RT molarity concentration times real gas constant times T is equal to the osmotic pressure. For example, 1 mole ቢሆን assume there is 1 mole and volume ደግሞ 1 liter ቢሆን, so N over V, this is real gas constant, and this is the temperature at 25 degrees centigrade. I mean, this is at 0 degrees centigrade. I mean, 273 degree Kelvin, 0 degree centigrade ማለት ነው. So at 0 degree centigrade, yes, it gives this osmotic pressure. So the osmotic pressure of the right and the left side, እዚህና እዚህ ጋር ያለው osmotic pressure ይለያያል. Due to this difference, solvent molecules migrate from one side to the other in order to dilute the concentrated parts. So biologists and biochemists often take advantage of osmotic pressure when they isolate the component of cell. cell componenቶችን ለመለየት ይህን osmotic pressure principle ይጠቀማሉ። እንግዲህ ታች ክፍል ላይ osmosis እና diffusion ተብረናል. Osmosis is the movement of particle from low concentration to high concentration እንላለን. And diffusion is the movement of particle from high concentration to low concentration in the gas. The medium is gaseous medium, for example, in the diffusion. Diffusion also happens in liquid medium actually. ማር አይበላሽም እንላለን። ለምን ይመስላችኋል? ማር አይበላሽም ብዙ ጊዜ ውሃ ካልተጨመረበት ማር ለረጅም ጊዜ ይቀመጣል ሳይበላሽ ይባላል። ለምንድነው? ባክቴሪያዎች ማሩ ላይ ሲያርፉ ባክቴሪያ እንግዲህ ታውቃላችሁ ውስጥ ያለው ኮንሰንትሬሽን የግሉኮዝ ኮንሰንትሬሽን እና ውጭ ያለው የሹገር ኮንሰንትሬሽን እኩል አይደለም። ባክቴሪያ እንግዲህ ሜምብሬን አለው። ሶ ኤክስተርናል ኢንቫይሮንመንቱ እንግዲህ ማር ላይ ሲያርፍ ሃይ ኮንሰንትሬትድ ነው ማለት ነው። ኢንተርናል ኢንቫይሮንመንቱ ወይም ሴሉ ውስጥ ከሴል ሜምብሬኑ ውስጥ ያለው low concentration. So naturally osmosis happen ያደርጋል ማለት ነው። እዛ ባክቴሪያ ሴል ላይ ምን ማለት ነው? ከውስጥ ወደ ውጭ እንግዲህ the movement of solvent particle from low concentration to high concentration osmosis ያካሄዳል ነው። So የባክቴሪያው ፍሉድ ወደ ውጭ ይወጣና ባክቴሪያው አውቶማቲካሊ ፍላሲድ ይሆንና ይሞታል። So that ባክቴሪያ ፕሮፓጌት ማድረግ አይችልም ማለት ነው ማር ላይ። So due to high concentration of sugar in honey, it can kill bacteria naturally due to this osmosis process. Okay, osmosis process happen ያደርግና ባክቴሪያው ፕሮፓጌት አያደርግም። instead flaccid ይሆናል ማለት ነው። ሶልቨንት ሞለኪውሎቹ ከሴሉ ወደ ውጭ ወጡና ተጨማጥሮ ባክቴሪያው ይሞታል። So that the honey cannot be can keep for a longer period of time as far as it's kept in a clean environment. Okay, so ይህን principle እንግዲህ biologists and biochemists this cell ላይ ይጠቀማሉ. So as the cell membrane is equivalent to semi-permeable membrane, cell membrane የምንለው እንደ semi-permeable membrane function ስለሚያደርግ ነው። ሶልቨንቱን ያስወጣል፣ ሶሉቱን ግን አያስወጣም ማለት ነው። All right, this is all about chapter 2. Thanks for today. This presentation helps to master your subject matter. Please don't forget to subscribe the channel. የሚቀጥለውን ፓርት ስለቅ እንዲደርሳችሁ ሰብስክራይብ ማድረግ እንዳትረሱ። Goodbye.